So this is the module 4 once again. We'll be discussing on the high frequency response of an BJT amplifier which comes under the sub module 2 of module 4. So high frequency response, here you can see a BJT transistor model is given, and these are the capacitance, these are the junction capacitance which are acting between the base and the collector and the base and the emitter. So we have to see at high frequency response how does this junction capacitance affect the frequency response of the amplifier. So at high frequency, the internal transistor junction capacitance do come into a role, reducing an amplifier gain and introducing a phase shift as the signal frequency increased. So in a BJT, CBE is the base to emitter junction capacitance, CBC is the base to collector junction capacitance, and output to input capacitance. So at low frequency, the internal capacitance have a high reactance because of their low capacitive value, usually in few picofarads, and the low frequency value. Therefore, they look like open and have no effect on the transistor performance. So as the frequency goes up, these internal capacitive reactances due to CBC and CBE goes down, and at the same point they begin to have a significant effect on the transistor gain. So just take an example over here. Here we are giving a AC signal. So because of this resistance RS, which is a source resistance, you can see that voltage has slightly decreased. Now this CBE will again act on it. So this is nothing but a low pass filter, and this is going to add up. This whole capacitance RC combination will add up, and we'll try to understand how this gain is, the magnitude of this voltage VB is going to settle. Okay, so this is here showing you the effect of CBE. In this figure it is showing you the effect of CBC. This is the input signal. This is how that voltage voltage drop across RS has affected, and a combination of these two is going to get you this signal. Now here signal is amplified certainly, but this capacitance CBC is going to drop down the magnitude of this output voltage. Okay. So when the reactance of CBE becomes small enough, a significant voltage is lost due to the voltage divider effect of the source resistance of CBE, which is shown over here. When the reactance of CBC becomes small enough, a significant amount of output signal voltage is fed back, a negative feedback, and thus the overall gain will reduce, voltage gain will reduce. We are going to study the effect of Miller capacitance. So assume that this is an amplifier with a gain, negative feedback gain, with a gain negative, and this is the capacitance CF connected over here. So what will happen is that this capacitance, which is between the input and output, it needs to be broken down in order to understand the effect of this capacitance, which is at the feedback between the input and output. So here we apply the Miller's theorem. So Miller effect occurs only in inverting amplifier. It is the inverting gain that magnifies the feedback capacitance. Okay, so current is II, we are deriving it actually. So VII is equal to V in minus AV V in upon XC. So this is a simplified version of it. V in is 1 plus A into twice pi F into CF. So what will happen is that the impedance that we get, take the ratio of the above relation, and we get an impedance of twice pi F into C in. So which is nothing but an impedance due to your capacitance as input capacitance. So C in is equal to 1 upon A times CF. So this is shown over here. Similarly, we will have to find out the output capacitance CO due to Miller capacitance CF. So in this way you calculate the capacitance C, which is given as AV plus 1 upon AV. So here you have to slightly just understand that if there is a negative feedback, negative gain or a negative feedback of an circuit, then only we apply the Miller's theorem. Otherwise we need not. Okay. For example, if say CBC is present between the base and the collector junction, but if the gain of the system is positive, then we need not apply the Miller's theorem. You will come to know when we are solving our example. Fine. So Miller's theorem is used to simplify the analysis of inverting amplifier at high frequencies where the internal transistor capacitance are important. AV is the voltage gain of the amplifier at a mid-range frequency and C represents the CBC. So Miller's theorem at C effectively appears as capacitive from input to ground and is given as C in Miller is equal to C into AV plus 1. Miller's theorem also states that C effectively appears as an capacitance from output to ground and is given as C is equal to AV plus 1 upon AV. This indicates that the voltage gain is greater or equal to 10. So C output is approximately equal to CBC because AV plus 1 upon AV is equal to 1. So high frequency response of common emitter amplifier by using the Miller's theorem. Now here in this particular configuration you can see that here we are considering only an AC circuit. So here all the DC sources are shorted. Okay, and here respective capacitances are shown CBE. Now whatever was the capacitance existing between the base and the collector terminal, it is treated as a Miller capacitance C and will be broken down into C in Miller and C out Miller. Let us go ahead for analysis of this. So high frequency response of CE amplifier constitutes of two parts, one at the input side and another at the output side. So we will be calculating the upper higher cutoff of frequency and at the input and the higher cutoff frequency at the output due to capacitance CBE and C in. Okay, and here we are going to calculate the higher cutoff frequency at the input due to CBE and C in Miller. Here C in Miller at the output is directly equal to CBC since the voltage gain of the amplifier is unity or 1. So as the frequency increase, the capacitive reactances become smaller. This causes the voltage at the base to decrease. So the amplifier voltage gain decreases. The reason for this is that the capacitance and reactance act as a voltage divider, and as the frequency increase, more voltage is dropped across the resistance and less across the capacitance. So at higher frequency response of CE amplifier at the input circuit, your capacitance impedance is given as 1 upon twice pi FC into C total, where C total is CBE plus C in Miller, and this comes out to be approximately RS parallel R1 parallel R2 parallel beta AC, and this is that impedance at which you have to find out the cutoff frequency. So FC is equal to 1 upon twice pi R into C. So just remember over here, you need not memorize it. So 1 upon twice pi RC, map that R is equal to RS parallel R1 parallel R2 parallel beta RE, and the total capacitance C is equal to the CBE, which is a base to emittance capacitance, and the Miller capacitance CE, which is equal to CBC into 1 minus AV. So as the frequency shown in above goes above in the input RC circuit, causes the gain to roll off at the rate of minus 20 dBs per decade, just as with the low frequency response. So phase shift at the input circuit, this is given by theta is equal to RS parallel R1 parallel R2 parallel beta AC RE upon XC. So as the frequency increases above FC, that is a higher cutoff input frequency, the phase angle decreases. Phase angle increases above 40 degrees and approaches to 90 degree when frequency is sufficiently high. At the critical frequency FC, the phase shift is 45 degrees with the signal voltage at the base of the transistor lagging at the input signal. So next, second step, high frequency response of CE amplifier at the output RC circuit. So this is your output circuit, which is a combination of C out given by the Miller and the load resistance, and here the DC is shorted to perform. Now this circuit is totally ready for AC analysis. So output part of the AC analysis circuit is drawn here. Okay, so when you are finding out the total load resistance, this is open circuit, this is open circuit. So your total load resistance RAC is RC parallel R1, which is shown over here. Okay, and now this is a simplified version of this complete circuit. So it is working as a low pass filter here. So critical frequency is determined in the following equation here. So Fc is equal to 1 upon twice pi RAC into C out Miller. So now here C out Miller is, once again I am repeating, C out Miller is equal to CBC. Okay, why? Because the gain of this particular device is positive and not negative. Okay, second step which I am once again recalling, that if this device is having a negative gain, then our whole process of making it to work as an amplifier fails. So remember this. So twice pi, this is okay, that is already discussed. So phase theta is tan inverse of RAC upon XC Miller at the output. So total high frequency response of CE amplifier here, this is the total frequency response of CE amplifier. This was in the mid gain. Now here this is coming because of your input RC circuit, and this is coming because of an output RC circuit. So here the roll-off rate is reduced by minus 20 dBs per decade. That means your voltage gain is reducing by minus 20 dBs decade, and then another RC circuit, because of an output RC circuit in our CE amplifier, it is further reduced to minus 40 dBs per decade. So this plot which is shown is an ideal one, whereas in practical case we generally consider a mid-band gain which is considered as an minus 3 dB from the actual mid-band gain that we have considered. So here is your actual cutoff frequency. Right? Whatever the explanation I have given, I'll just read out from the slide. Two RC circuits created by the internal transistor capacitance influence the high frequency response of BJT amplifier. As the frequency increases and reaches the high end of its mid-range value, one of the RC will cause the amplifier gain to reduce and drop off. The frequency at which this occurs is the dominant frequency Fc. It is the lower of the two critical high frequencies. So at Fc input, the voltage gain begins to roll off at minus 20 dBs per decade, and at a critical frequency at the output, the gain begins to drop at the rate of minus 40 dBs per decade, because of each RC circuit is providing a minus 20 dBs per decade roll off. So this is the overall frequency of CE amplifier. This comes because of the capacitance, coupling capacitance SCC and CE. Mid-band gain, there are no capacitance as they are neglected. So it remains sufficiently stable. At high frequency, the gain is falling because of the junction capacitance CBE and CBC and CCE. Okay. So network parameters, let us try to understand this practically in our CE amplifier. So this is your CE amplifier shown over here. Capacitance is CWI, CW0. This is your base to collector capacitance, base to emitter junction capacitance. capacitance between the junction collector and the emitter. Fine. Now this capacitance CS and CECC, they don't play a vital role when you are considering a high frequency response analysis. Okay. So this is your AC analysis circuit, which will first help you to find out the input capacitance, as well as your majorly your resistance R. So it's a combination of R1, RS parallel R1 parallel R2 parallel beta RE fine. So the capacitance, input capacitance, since they are all in parallel here, you consider CI, since they are all in parallel, CWI, CBE plus the Miller capacitance, which is given as 1 minus AV into CBC. So from here you make a note that CBC is the feedback capacitance. Okay, so it is adding to a Miller capacitance, and then at the input side it is written as 1 minus AV into CBC. So that forms a input capacitance CI, and you can find out the value of FHI, which is the higher cutoff frequency at the input side. Okay, then coming to the higher cutoff frequency at the output side, just try to analyze what is the resistance present at the output side. So here you can see from the circuit, this will be open circuit. Okay, capacitance will be also capacitance offers a low impedance at higher frequency, so this will be open circuit. So your overall output impedance RTH at the output is RC parallel RL parallel R0 over here. Okay. So after knowing the total Thevenin's resistance at the output, we will find out the capacitance C0. So C0 is a parallel combination of CWO, then C, CE and CMO. CMO is the Miller capacitance. So here it is expressed. Now this gain AV is almost equal to 1. So this particular factor will cancel out, and this whole term will reduce to CBC. Okay, so Miller's capacitance at the output is straight away equal to CBC. So your overall output capacitance, since they are in parallel combination, we add them. So CW0 plus CCE plus CBC. So you know these two parameters RTHO and CO. Substitute in this relation, that is 1 upon twice pi RC, and find out the higher cutoff frequency due to the output RC circuit. So we'll find out the gain. The gain at midband is HFE mid upon 1 plus J times F upon F beta. The quantity F beta is determined by the set of parameters employed in the hybrid pi model. So F beta K is oftenly appearing as FHFE, which is 1 upon twice pi R pi into C pi plus C mu. So F beta is a function of bias configuration. The small value of HFB from the chosen frequency range reveals that the common base configuration displays an improved high frequency characteristics over common emitter characteristics. gain bandwidth product. Let us try to understand what is a gain bandwidth product. It is an quality factor for determine the performance of your amplifier. So it's a figure of merit, which is also called as an gain bandwidth product, and commonly used to investigate the design process of an amplifier. So it's a quality control process now. So it provides an important information about the gain of an amplifier and the expected operating frequency range. Okay, so here for two particular different gains we have plotted the frequency response. So here cutoff frequency, here bandwidth is 1 megahertz, and here the bandwidth is 10 megahertz. So this particular whole range is trying to make us understand how the amplifiers at different voltage gains they work and what is the frequency range. Okay, so bandwidth here, lower cutoff frequency, higher cutoff frequency. So FH minus FL is equal to FH. Your FT, which is going to be the gain bandwidth product, it is equal to AV mid into FH. FT is also called as a gain bandwidth product frequency range. So higher cutoff frequency FT, which is defines your unity gain frequency, or we can also say the frequency FT is at the gain bandwidth product. So FT is equal to HF into F beta. So F beta is 1 upon twice pi HFE mid into RE into C pi plus C mu. So in terms of F beta, it comes out to be this much, 1 upon twice pi RE upon C pi plus C mu. This will be very helpful for the analysis or for performing the overall analysis of the system in terms of gain and the frequency range. Reference chapter 9 of Boylston Electronic Device and Circuit, 11th edition, Prentice and Hall. So discussion based on the previous extract of this session. Step 1, find the Miller capacitance CMI and CM0 on the input and output side due to the capacitance CBC. Find the total capacitance on the input due to CBE, CMI and the total input resistance. Find the higher cutoff frequency FHI and the gain AV. Step 2, find the total output resistance due to total output capacitance due to CMO, which is the Miller output capacitance, and CCE, junction capacitance between the collector and the emitter, and the total resistance at the output due to R1, R2, beta RE, RE and RL. Of course, RO has to be included here. Find the output higher cutoff frequency FHO and the gain AV. Step 3, select the highest frequency among FHI and F0 and plot the frequency response Bode plot. To have a better understanding of high frequency analysis, we'll discuss one example based on this. So here is the example. So for the given network, here we are including RS and VS. Determine the higher cutoff frequency FHI and F0. Find F beta and FT, that is the gain bandwidth product. Sketch the frequency response using a Bode plot. And what is the gain bandwidth product? Here you have to explain in literature because we have already found out FT. So here this circuit is there. What are the things given here? CWI, CWO, this is already given. So CBC, CBE and CCE. Okay, so for a common emitter amplifier, Miller capacitance not being very effective at higher frequency range, it is not considered, okay, because it is stable and doesn't provide a negative gain, that is why. So from DC analysis, we will find out the value of RE, that is the relation of DC analysis and AC analysis. Because we need the parameter RE, we have to first do the DC analysis. And for finding out RE, we need to find IE, which is done over here. Then cutoff frequency FHI, what is required is we have to find out the input capacitance CI and RTHI. So CI is nothing but the whole combination of CWI, CBE and CBC. So 5 peak, these are the values given in the problem. Substitute them, you get an approximate value of 57 picofarad. Then input resistance over here is beta RE. ZB first I am calculating. So ZB is occurring over here. Beta RE plus beta plus 1 RE parallel RI, since this current source is open circuit. Okay. So ZB is this much, which is calculated, and then we calculate RTH by taking this relation RS parallel R1 parallel R2 parallel ZB. Okay, this is slightly different because we have connected a resistance RS over here. Next, FHI comes out to be 3.4 megahertz after substituting the value of RTH and CI. Second, we are finding out the higher cutoff frequency at the output. So 1 upon twice pi RTHO upon CO. So RTHO is equal to RE parallel RL parallel RC parallel RE parallel R1 parallel R2 upon beta. So it comes out to be this much. Step by step it is done. First I have calculated this ratio. Okay. Then I have taken a parallel combination of these two, found out this relation. Taken the parallel combination of these two, found out this, and then a parallel combination of 1.2 in parallel with 0.38 ohms. So it comes out to be 535 ohms. So C0 is equal to CWO. This is given in the problem statement. Even CCE is given in the problem statement. So combine them, you get 16 picofarad. As I said, Miller capacitance is straight away ignorable because here the gain is greater than 1, or you can say greater than 10. So FH is equal to 9.9 megahertz. So gain bandwidth product, it was mentioned just to state the relation. So AV mid into bandwidth. So bandwidth is FH minus FL. So this completes my problem analysis over here. This is the overall view of how the steps are calculated. This is step 1 where the problem statement is given. Step 2 where you're finding out RE. Then we are trying to find out the higher cutoff frequency due to the input RC circuit here. RS and capacitance CBE and CBC in this step. Okay. The step 2 we are trying to find out the output cutoff frequency because of this RC, because of this C and R combination. Fine. So all these are working as an low pass filters here. So here this is your mid band frequency that is calculated, which is around 1 kilohertz, 1 megahertz, and your approximate gain, approximate frequency at which the gain starts falling is 100 kilohertz. Here it is shown, and this is the Bode plot. And finally, this is the last statement where you have to simply define what is your actual gain bandwidth product and what is your bandwidth frequency. So next video session will be helpful for understanding how the numericals on high frequency response of CE amplifier is being performed. First video slide will first video session will show you how and high frequency analysis is done, relatively different from what approach I have used, but theoretically they are same. Then only representation will vary, and then the problem based on this.
Welcome back. Now we're going to take a look at the high frequency response for a common emitter amplifier circuit. And again, that's just in general terms, not a particular example, so I haven't entered any values. So we're just going to come up with general expressions. But again, the important thing is that you get familiar with the process of determining, what are the capacitances that you need to consider, how do you calculate them, how do you calculate the Thevenin resistance across those capacitances. So high frequency response for this common emitter amplifier is just the same one from the previous example. Now, in order to consider the high frequency response, I'm going to go ahead and draw the AC equivalent circuit, just so that we're properly ignoring the coupling and bypass capacitors, as well as DC sources and things like that. So let me go ahead and, so this will be VS. So you could call this my high frequency equivalent circuit, I suppose. Then you have, so this is RS, this is the parallel combination of R1 and R2. I'm gonna combine them since they're both going to signal ground. Then I have my BJT transistor. At the collector I have resistor RC connected to ground. I'm shorting through the coupling capacitor. This is RL. This is CL. That's V out. And then in case of my emitter, I am shorting through CBE, and so it's just a direct short to ground. Now let's go ahead and include the capacitances that are going to play a role in our high frequency response. I've already included CL. And then we're going to have, I'm going to draw them in orange because I'm going to be sort of modifying them a little bit later. But we have, if you remember, CBC and CBE, right? CBE is simple. It's just a capacitance between the base and ground, because the emitter is directly connected to ground. So I'm going to go ahead and just replace that with CBE to ground. Now this CBC capacitance is a feedback capacitance in this case, because this is a common emitter amplifier. We're applying the input signal at the base, we are taking the output out of the collector, and that capacitance happens to be connected between base and collector, between input and output, and is therefore a capacitance in the feedback path, which is going to be affected by the Miller effect, meaning that capacitance is going to appear as two shunt capacitors, one at the input, one at the output, of values. The one at the input is going to be multiplied times the gain of the amplifier. The one of the output is going to have approximately the same value as CBC. So I'm going to split that. I'm going to call this one, in order not to crowd my circuit here, Miller input capacitance, and the one at the output is going to be Miller output capacitance, CM output. So I'm going to delete this one since I've replaced it. Oopsie. All right, so this will be my, my high frequency equivalent circuit now. And I'm in a good position to start considering my high cutoff frequencies. I'm going to consider first the one due to the capacitance connected to the base, and then the one, or at the input, and then the one due to the capacitance connected at the output. Now, you may say, well, there are 4 capacitors here, and I just noticed I wrote CL as a resistor, but that's actually a capacitor. You may say there are 4 capacitors here, shouldn't we have 4 high cutoff frequencies? But notice that, you know, they're connected in parallel with each other, so CMI is connected in parallel with CBE, so the parallel combination of the two is just going to be equal to an equivalent capacitance of value equal to CMI plus CBE. In other words, I can combine these 2 capacitors as just being one capacitor value CMI plus CBE. And the same happens with CMO and CL. I can just combine them, and the parallel combination of 2 capacitors, the equivalent capacitance is equal to the sum of those capacitances. So in all reality, you can see I have just 2 capacitors. So let's go ahead and consider FH1, which is going to be due to the input capacitance. So I'm just going to label it FHI for input. This is going to be equal to 1 divided by 2 pi R Thevenin I will call it, CI for C input capacitance. Where I have already determined that my input capacitance is the sum of the Miller input capacitance and CBE. And the Miller input capacitance is going to be equal to CBC times 1 minus A plus CBE, or approximately equal to the absolute value of the gain times CBC plus CBE. And the reason for that is the gain for a common emitter amplifier is typically much larger than 1. My R Thevenin input will be the equivalent resistance connected across the terminals of that capacitor. So if we look at our high frequency equivalent circuit here, we will see that we have R1 in parallel with R2, and all that in parallel with RS. And again, I am turning off my voltage source VS, so that's just a short to ground. So it's basically R1 in parallel with R2 in parallel with RS. That will be the value. Oh, and I'm missing one. And the one that's connected on the other side, which is going to be beta times little r. And now I think I've got all of them. So that will give me a value for high cutoff frequency FHI. I can reproduce that methodology for my output capacitance and come up with another high cutoff frequency to the output capacitance. 2 pi R Thevenin seeing across the terminals of the output capacitance times the output capacitance, where my output capacitance is the combination of the load capacitance and the Miller output capacitance in this case, so CMO plus CL. And CMO is going to be equal to 1 minus 1 over A times CVC plus CL. And again, since the gain is typically much larger than 1 for a common emitter amplifier, we can approximate this as CVC plus CL. And now the Thevenin resistance across the terminal of that capacitance is just going to be from the schematic or from the drawing, RL in parallel with RC, and if we want to consider little rho, it will also be in parallel with little rho. So RL in parallel with RC in parallel with little rho. And then I have two values for the two frequencies where I have my two poles, the one introduced by the input capacitance, the one introduced by the output capacitance, and I can consider my overall FH to be equal to the lowest or the minimum between the two, FHI, FHO. Now, if you're a little bit confused as to the process and how we came up with some of the resistances and so forth, don't worry, just keep going, because we're going to see several examples with actual circuits, common emitter, common base, common collector, and I think that by doing a few of them in actual examples with actual values, hopefully you'll get the hang of it. So, thank you. Hello. Finally, we are going to calculate the higher cutoff frequency for this common emitter amplifier, and that is FH. Now, in order to do that, I'm going to draw the high frequency equivalent circuit, just because it's going to allow us to see things more clearly. So let me go higher cutoff frequency. FH. And again, I'm gonna just redraw the circuit, the high frequency equivalent. So this is VS, there is RS in series. Just to make things a little bit more compact, I'm going to lump R1 in parallel with R2 into a single resistance. And then this is fed into the input of, or the base of my transistor. My base is connected to the emitter resistor RE1. My collector is also connected to ground via a collector resistor. And then my output is taken here, and I'm going to go ahead and, since we've added a large load resistor, I'm going to go ahead and include it here. I may as well just connect both of those in parallel, so let me do that, maybe more clear. So I'll have my RC going to ground, as well as my load resistor going to ground, and then here will be my output, V out. I have replaced all my bypass and coupling capacitors with short circuits, because now we're considering the high frequency region. And the other thing I need to include now are the capacitances that are going to affect the high frequency response. And those are going to be any internal capacitances of the transistor, as well as load capacitances, parasitic capacitances, etc. There are two internal capacitances. One of them is CVE, and another one is CVC. Or if you look at the data sheet, they will appear as input capacitance C IBO and output capacitance C OBO. That's what I've labeled them up there. And they're also sometimes referred to as C mu and C pi. C pi will be the one connected to the emitter, and C mu will be the one connected to the collector. And now I'm going to note that my CBC capacitor is connected between input and output, and so this is actually a feedback capacitor. And it's going to suffer from the Miller effect we have talked about, meaning any capacitor that is connected in the feedback path of an amplifier, meaning between input and output, it's going to appear as if there were two shunt capacitances, one at the input, one at the output. The one at the input will be equal to the actual capacitance in the feedback times the gain of the circuit. The one at the output is approximately equal to the feedback capacitance. So I'm going to do that change here. I'm going to replace that CBC capacitor with two shunt capacitances. One here, which I will call C Miller input, and one at the output, which I will call C Miller output. And with that, I'm gonna delete CBC. Because I've already replaced it with those two equivalent capacitances. Now for my CBE, it's really not directly connected to ground since I have the emitter resistor RE1. However, to simplify my calculations, I'm going to go ahead and assume it's connected to ground. If you do the calculations, you'll see that there's going to be not much of a difference in your result. But if you want it to be proper, you will need to analyze the circuit with that connection to the emitter instead. Myself, I'm just going to make the approximation that this is connected to ground, and therefore it's going to be in parallel with the Miller input capacitance, and so I'm going to consider my overall input capacitance to be equal to the sum of the two parallel capacitors, C Miller input plus CBE. So I'm just going to eliminate this and say, oops, plus CBE. And my output capacitance will be C Miller output. I did not consider any load capacitances, but if I had any load capacitance, I will just be adding it to CMO, to the output Miller capacitance. All right, so let's go ahead with the calculations. We have an input capacitance and output capacitance, and so two contributions to our high cutoff frequency. I'm going to refer to the one due to the input capacitor as the input high cutoff frequency. Value is going to be equal to 1 divided by 2 pi RC, where C will be my input capacitance. Just going to refer to as C input. We'll calculate it separately. And this will be the Thevenin resistance connected to that input capacitance. So C in this case is C Miller input plus CBE, and R Thevenin input is going to be whatever is connected to the capacitance, which will be RS. Again, we're going to short through VS, and so that will be RS to ground in parallel with R1, in parallel with R2, in parallel with little re plus RE1. So RS parallel R1, R2 in parallel with beta times little re plus RE1. I'm going to calculate that value separately. So RS will be 1 kilo ohm in parallel with 220K, parallel with 20K, in parallel with 100 times little r is 50, RE1 is 150, so that's 200. and that's going to be equal to around 900 ohms. Notice that it's going to be dominated by the 1K resistor, the source resistance, since it's the smallest. I can also calculate my input capacitance separately. My Miller input capacitance is going to be equal to my CBC capacitance times 1 minus the gain being negative 100, plus CVE. And so in this case, it's going to be my CBC, which was 4 picofarads, times 101, plus CVE, which is 8 picofarads. And that's approximately 412 picofarads. And now I can enter those values into my equation here. 1 over 2 pi 900 times 412 pico. And that's approximately 430 kilohertz. And finally, my high cutoff frequency due to the output capacitance, FHO, could be similar expression, 1 over 2 pi RC. In this case, C will be the output capacitance, and this will be the Thevenin resistance seen across that output capacitance. C out, in this case, is just going to be CMO, the Miller output capacitance, which is going to be CBC times 1 minus 1 over A, which is approximately equal to 1. So this is approximately equal to CBC, which is 4 picofarads. And the Thevenin resistance connected to the output is going to be RC in parallel with little r, the output resistance of the amplifier, in parallel with the load resistor in this case. So RC was 20K, in parallel with 200K, in parallel with 100 meg. We can see that RC is going to dominate that parallel combination, so that's approximately equal to 20 kilo ohms. So 1 over 2 pi 20K times 4 picofarads yields 2.48 megahertz. Approximately. All right, and now, just like we did before, we are going to use the dominant pole approach, and so we're going to approximate the high cutoff frequency as the minimum of FHI FHO, which in this case is just FHI, which is 430 kilohertz. And that's it. That completes our analysis here. I'm going to write here higher cutoff frequency. FH equals 430 kilohertz. And I'm going to highlight the results of, quiescent current, mid-band gain, input resistance, output resistance, as well as low and high cutoff frequencies for this common emitter amplifier. Before we go, a few things to note. Note that the dominant high cutoff frequency in this case is the one due to the Miller input capacitance. That's the one that has a highest effect on the high cutoff frequency. It's the largest. You can see it's around 400 picofarads because it is 4 picofarads multiplied times the gain of the circuit, which is 100. And that's typically going to be the case for a common emitter amplifier and for any amplifier that has a feedback capacitance and a high gain. the Miller effect is going to make that capacitance a lot higher than most of the other capacitances in the circuit, so it's going to dominate the frequency response and limit the bandwidth of the amplifier. Thank you.